Here in the second part of online lecture 6, we'll focus in on map projections. So why do we need projections for maps? First off, we can't carry globes around. They're very accurate. Well, they're moderately accurate, but they're bulky and obviously awkward to carry. Further, projections help us to make measurements and chart courses. It's a whole lot easier. Even further, they're smaller in size. You can fold a map. They're cheap, but there's a big problem. They always introduce some type of distortion. So there's always some way in which they have a flaw. Let's get through some key terms. First off, a reference globe is the final size of an imaginary globe, which is set according to the principal map scale. And so what you have is you have a particular reference globe in which you then will put on top of that what we see next is a developable surface. So this is a mathematical surface that can be flattened to form a plane without compressing or stretching any part of the original surface. And so the key thing with these maps, all these different projections, as you're going to see, what they're attempts to take that round Earth, the reference globe, and to flatten it into a piece of paper, into a map, into a computer screen, without causing it to stretch or compress in any way. And so there's three different types. There's one in which we use cylinders as our developable surface. There's others where we use cones, which is called conic, and another one which is where we use a flat surface or planes, and we'll call those planar and azimuthal. So here we have the reference globes are shown. The reference globes there, those are what I'm referring to as a reference globe, and each of these are the developable surface. So we have the first one, planar, second one, a cone or conic, and you can see how it produces a particular outcome, very distinctive shape. And then finally a cylindrical, where essentially we take a cylinder as our developable surface and put it around our reference globe. So once again, decisions, decisions, decisions. Which one do you choose? There is some logic, once again, to this decision. So we'll see, some guidelines, some good suggestions, and some bad suggestions for particular map projections. And as most cases, there's a best projection for us to choose based on the data that's being mapped or the area that's being mapped. So cylindrical projections, they are of course the result from wrapping the developable surface of a cylinder around a reference globe, then projecting the land masses in graticule and unwrapping the cylinder. Lines of longitude typically appear straight and are equally spaced. Lines of latitude are also straight, but they are not equally spaced. Further, the lines of latitude and longitude, one key characteristic is they intersect at right angles. A conical projection is one that results from the wrapping of a developable surface of a cone around the reference globe, projecting the land masses in graticule onto the cone, and then unwrapping the cone. So we can kind of see how that unwrapping happens here. Longitude lines appear as straight lines that are of the equal length and radiating from a central point, whereas latitude lines appear as concentric circular arcs that are centered around, in this case, the North Pole. And we see this distinctive shape of a pi wedge with a conic projection. These are typically best for mapping things here in the middle latitudes on both sides of the equator. They typically are good with things that have an east-west extent. So if I was mapping, let's say, Russia, or maybe China, or the United States, that have a very much a east to west layout, then I would definitely consider using a conic projection for my map. Finally, we have our planar projections. This results from the positioning of a developable surface of a plane next to a reference globe and projecting the landmass and graticule onto the plane. The longitudes appear as straight lines that radiate from the center. Latitudes appear as circles centered around a point, in this case being the North Pole. And there's two different ways in which we can further take projections. And first off, we'll have the case of projection. And that's the positioning of the developable surface relative to the reference globe. So we have the first one is called a tangent. That's where the reference globe touches the developable surface along only one line or at one point. We'll also refer to this as simple. For example, a simple line or a simple point. A secant is a developable surface that passes through the reference globe. I have illustrations that will follow that help to showcase this, and we'll also refer to these as standard lines. Points of tangency, or where the reference globe touches the developable surface, are called standard points. One of the characteristics is the areas between standard lines projected to the developable surface will have a compressed scale. In other words, things will be closer together than what they are in reality, whereas areas beyond the standard lines have a more exaggerated scale, where things are farther or more spread out than they otherwise would be. Here's what I mean by tangent. You can see this cylindrical situation here where it's touching just right there. So this tangent is, in this case, the equator. And so it's touching on both sides, where here it actually cuts through, and actually doesn't really cut through, but it goes through the reference globe. And so once again, our developable surface is the cylinder, and our reference globe is, of course, the circular object. And so this would be secant, in which it has, in this case, two standard lines. Here we have the conic and the tangent in this case. The tangent is just right there. Essentially, the cone is placed right on top, so the cone is right there above the poles, above North Pole. And then here we have a secant situation where we have a standard line and another standard line, as the developable surface essentially goes through the reference globe in two locations. And then the planar class here, we see a tangent where it just is at one particular point, in this case the North Pole, or a particular secant where you essentially bring that developable surface down into the reference globe, and we have one particular standard line now. Okay, so in the case of the projection, we were interested in, okay, is it touching just one particular location, one particular latitude, or is it a situation where we have a secant, where we have the developable surface is actually positioned in which it's intersecting twice with the reference globe. Now the aspect of projection is, okay, now we're going to move it around. Move the projection, move it up and down as far as along the equator, mid-latitudes. And so now this is going to be more focuses on the where. First off, we have some terminology. And so when we hear the term normal, you might also hear the word equatorial, and that's an aspect somewhere along the equator. A transverse, or a polar, sometimes called polar, is an aspect which is somewhere on one of the poles. An oblique is an aspect somewhere between a pole and the equator, for example, the mid-latitudes. Let's take a look at this. These are all previously seen. These are all from a previous slide, and these are all examples of what we call a normal aspect. So the cylindrical normal aspect is there along the equator. Thus the name, that's why we see equatorial. Now, it's not probably the best term to call it equatorial, because this whole group, all of these are normal, because you'll see the next two are actually used the poles. And so here we see the conical normal aspect is above the North Pole or the South Pole, and the normal for the planar azimuthal is also polar. Now here's an illustration for the transverse for the cylindrical, and we can see right through here the tangent is at one of the poles. And so what that means then is for the planar and the conical, the equator is the location for the transverse aspect. And then now you see how the cylindrical here, we have the oblique, and so now it's somewhere in between the equator and a pole. So it's somewhere here in the mid-latitudes. And for both the conical and the planar, the mid-latitudes are also used, or the in-between area between the equator and the poles are also used for the oblique. Now the most important part of projections is understanding their distortion. All flat maps have some type of distortion. It's important to know about the pros and cons of each projection as you determine which is best for whatever you are mapping. Think of distortion as the cons or the negatives for a particular projection. For example, questions to ask. Is your map of a small area or region, like Indiana? Are you using global data and wanting to show land area data across the world? Are you doing research in the Antarctic and want to show as much of the surrounding ocean waters as possible? You're not? Okay. Well, still, you'd want to consider the pros and cons of each projection as you decide which to use based on each of these individual questions I just asked. All of them you would have a different response. You would have a different projection in which you'd want to use. And I've showed this in a previous video. It's a cool way to essentially visualize distortion. We can see this quite obviously. There's a mathematical process to this as well. I'm not going to go too much into that. But here we see, in this case, different projections, and notice what it does to the human head. It changes it, it alters it in different ways. I'm not going to go too far in the weeds here, but in terms of distortion, there's a mathematical formula to actually measure it, and something called this scale factor. And it's essentially the local scale divided by the principal scale. The local scale is computed at a specific location, where the principal scale is computed at a standard point or along standard lines. Keep in mind those standard points, standard lines are key terms I mentioned a little bit earlier. And the result essentially is this. If your mapped area, if your specific location, if you have a scale factor that's greater than 1, that means it has an exaggerated scale. In other words, greater than 1 means objects are being shown in this area of the map as being bigger than what they really are. Whereas areas in which they have a mapped area, specific location, which it's less than 1, means it has a condensed scale. So there, objects are depicted as being smaller than what they are at that location. And of course, the closest you get to 1, that means no change in scale at that location, which is, of course, the ideal situation. We want to have as little exaggeration or condensing as possible. And I'm not going to go too much in this, but ArcGIS, what they do is they can show you a particular scale factor for a particular reference, projection, what have you. Here we have a cool term, an indicatrix. And so Nicolas Tissot developed the indicatrix, which provides a graphical representation of distortion at various points across a projection. So we're going to use a lot of these. So when we look at projections going forward, and we try to understand, okay, why is this a good one? Why is this a bad one? We're going to use this particular situation here where we have these different circles. And so what the circles mean is where we have perfect circles that are this particular size means we have very little distortion, where here you can see how the distortion causes things to get flatter and maybe a tad bigger. And so here we see how we have now oval features. And so the distortion for this particular map here is that we have, for the most part, in the middle looks pretty good. But when we get to the higher latitudes, both going towards the poles in both directions, things get a little bit more distorted. So now we can illustrate linear, angular, or area distortion for different types of map projections. Our first family is called the equivalent or the equal area projections. And these preserve areas throughout the projection. So that's what they're good at. Here you have areas, they are all true. They are all true to what they actually are, the proportions. Not so much the shape, but their proportion. How much land area they take up on Earth's surface, proportional-wise to everybody else, is true. And you'll notice that in the upper latitudes, so the areas farthest away from whatever our central meridian might be, the ellipses, what happens, they appear elongated in kind of an east-west direction and more compressed in a north-south direction. Now let me quiz you. Was this a cylindrical, a conical, or a planar? And just by the shape itself, it should be a dead giveaway that this is a cylindrical. And so it's a cylindrical projection, which it's equal area. So all of these particular land areas are true. This is really how big Africa is in relationship to Greenland. However, the distortion is quite clear. You can see how things get squished. The shape is most certainly not correct. This is not the accurate shape of Greenland at all. It is not squished like that. Even further, Antarctica is not shaped like this at all. So you can see how they're squishing or elongating at the east-west extents as we go to a higher latitude, both to the north and south. But we see, for the most part here along the equator, the circles are relatively good. And so here we see distortion increases as we go farther away from the equator, or in this case, our latitude of origin. Now I changed my latitude of origin, change it to over the United States, and so here we have an equal area projection. So now I changed the central meridian and the latitude of origin. So now I'm up here in the northern and western hemisphere as my center, and you can see as I go away in all directions from this particular location, this equal area, this equivalent map has distortion, in which it starts having spreading out of the east-west context. And I show this because, wait a minute, we just saw how the high latitudes have greater distortion. Well, it's all about where our centering is, where we have our particular aspect. What are we, we're having an oblique view. We are not using the polar or normal aspects. In this case, we chose an oblique aspect. This is a pretty good one, in which it does do a good job of kind of correcting some of the problems. Further, I also like the fact that it is an ellipse, so it's does kind of relate to the shape of Earth. And also, we do have, for the most part, a point in which we can see here. So that's something that's we might not always see on these types of maps, as you'll see later. But this is, once again, an equal area. This is called the Mollweide, M-O-L-L-W-E-I-D-E projection, in which it does a good job, once again, of distortion there along the equator. But things get a little bit more distorted as you get, in this case, farther away from the central meridian, which is the prime meridian, and farther away from the latitude of origin, the equator. So once things get farther away, we get a little bit more distortion. The hammer was kind of a reaction to the Mollweide, and so it's same idea, but notice what the lines of latitude kind of are played with here. And so now they're bending in opposite directions of each other instead of being straight lines all the way across. This is the sinusoidal. This is a little bit too, I don't know, maybe too much distortion. Maybe you like this. But here where we saw it was kind of a relatively a point. This is a clear point. The North Pole and South Pole are clearly observed points. But once again, based off of this particular projection here, we have a similar situation where along the latitude of origin in the central meridian, we see less distortion. But as we go farther away, things get more distorted. So this would be good if you have maybe a country. You could move the central meridian, move it around to where you have maybe a long north-south country. So if you move it over the central meridian to India, it would do a good job. Imagine if India was right here, it would do a good job of showing the true shape. But of course, since it's an equal area map, the correct area proportion-wise of the country of India. The last equal area that we're going to look at is called the Goods Homolocene. And this is a kind of a merging of a few of them. It merges the previous one here, the sinusoidal, and I think merges the Mollweide or hammer as well. But key here is it cuts out the oceans. And so where we would have really wicked distortion, see how you notice as you got further away, you got wicked distortion here. So essentially what it does is, okay, these places far away, we'll just cut them out. We'll cut out the extremely distorted places. And so that's how it kind of has a situation where we have a nice, pattern. We don't have as much distortion. The circles are relatively the same. So shape is a little bit more accurate here. Of course, direction's all screwed up because, the oceans aren't cut up like this. So direction, angular relationships are not shown at all properly. But this does do a good job of doing an equal area and for the most part showing the accurate shapes of different areas. But of course the negative is now, we've got things split up. Antarctica split up, Greenland split up. Next up, our family of maps projections are the conformal. These are good at preserving angles throughout the projection. And so only the angular relationships, not the shape, are preserved. And so here we're going to see large areas will have big time distortion, whereas smaller areas will have minimal shape distortion. And here's the world famous Mercator projection, which is an example of a conformal map projection. So using the Tissot circles here, whenever you see a particular projection in which the circles are all the same, some might be small, some might be big, but they are all the same. We don't see any ellipses. We don't see any flattening. We don't see any stretching north to south, east to west. These are all the same circles, just different sizes. So that's key to the conformal. We're going to have that's pattern. So I ask you, what kind of map projection was this? Was this done using a conic, planar, or cylindrical? Ding, ding, ding if you thought cylindrical because of the distinctive shapes. So Mercator is not only in the conformal family of map projections, it is also cylindrical. So it's a cylindrical conformal projection. Of course, the central meridian, you can choose whichever one you'd want. The latitude of origin is the equator, and the prime meridian is our central meridian. In the Mercator projection, what we have here is essentially these are infinity. These could go forever up here. So this is why Antarctica is massive, and Greenland is also relatively big. So here we see high latitudes once again are exaggerated. So our large areas, Greenland, Canada, Russia, look how much bigger they are than what they are in reality, especially compared to Africa. So this is the famous map projection that makes Greenland look just as big as Africa. Now, why would you want this? Well, you would want this maybe for navigational purposes because latitude and longitude, essentially every single one of them, are perpendicular. And so you can see they have right angles. And so when you're making measurements for navigational purposes as you sail across the ocean, this is actually a useful map. All right, type of Mercator projection, something called a transverse Mercator. So this is where it then takes those key terms I talked about beforehand. And here, the central meridian is, in this case, selected by the map maker. And in this case, I selected the one that relates to Indiana. So this is UTM NAD 83. UTM zone 16N. So that's what we use for Indiana. So the transverse Mercator, what it does is, it takes the benefits, the positives of this particular Mercator projection. The positives are if you're along the equator, if you're along the latitude of origin, right here in the middle, not much distortion at all. I mean, all things through here, the distortion is very, very, very minimal. So this is great for showing not only shape, but area, direction for things close to the latitude of origin. And so if I just essentially move that latitude of origin over here, and so I do a transverse, and so then I essentially transverse, flip it. So now I have the transverse going this way. Essentially now all places along this particular line of longitude, keep in mind over here, I just essentially flipped it, transverse, all points along here are going to be relatively accurate. There's going to be minimal distortion. And so this is why this is a preferred for things in small areas that have a north to south extent. And so what I can do is I can essentially then use the Mercator projection if I focus in just in Indiana, and I have a nice, good local projection that's going to show Indiana as accurately as possible. So I ask you, is this a conical, cylindrical, or planar? And by the shape of this, with this distinctive shape here, this is a conical projection. So this is a Lambert conformal conic. And so Lambert is the original person that came up with this. And so here, once again, we see the circles. They're all the same. We don't see any squishing. We don't see ellipses. All the circles are the same. Some, though, are bigger than others. And so as you go farther away, you notice how they get bigger and bigger and bigger. As you go farther away from this case, our particular aspect is normal. So it's above the pole. But it's centered here on the United States of America. That's why this is thus called the USA Lambert conformal conic, to be precise. And this here is the projection that you'll see used heavily in the United States. So you'll see it used in the USGS, uses them for their 7.5 and 15-minute topographic maps, for those of you who might work with those. It's also used for a lot of aeronautical charts. And the reasons are simple. Its directions are reasonably accurate. The distortion of shapes and areas is minimal at these particular standard lines, at these reference lines. In particular, the small areas. So if we zoom in, so if we do a large scale map, we zoom in, so that's why these are perfect for those very, very local township maps or topographic maps that the USGS and others use. This time I just changed the aspect to the South Pole. And so here we have South America. And so there would be probably two secant lines here. There are the reference lines that are helping to make this South America as little distortion as possible. And of course, as we go away, distortion increases. But that doesn't matter. All we care about is showing, in this case, what's as less distortion in terms of shape, area, direction as possible here in our focused area. We could care less about the other areas. We're just going to be using, in this case, super large scale, zoomed in on a particular small area. So this is a good idea in terms of type of map to use if you're wanting to map a certain small region or area in which you want to preserve as much as possible the angular relationships. Our next projection is called the azimuthal. These are going to preserve directions or azimuth from one central point to all others. And so that's where it's good. It's good at showing directions from a particular location or a particular center of a map to any other point from there. And this is the oldest or one of the oldest known projections. So the idea here is it's developed by placing a plane tangent to one point on the reference globe. Once again, that projection, that one point, is wherever you so choose. And it's at that point where the scale factor is going to be 1. All other locations, the scale factor is going to be greater than 1, and thus an exaggerated scale. This here is the azimuthal equidistant world map, in which the prime meridian is the central meridian, and the equator is our latitude of origin. And so the origin, or 0, 0, where these two lines overlap, where the prime meridian and the equator overlap, that is the center of our map. That's the plane tangent location. And from this point, in all directions, the direction is correct. You'll notice that it's definitely not equal area. The shapes get bigger. The circles get bigger and smaller, so it's not equal area. The shapes most definitely change. We see some that are circles, some that are ovals, so we see it's not conformal. And so it does a bad job of maintaining angular relationships, with the shapes really being distorted. However, the direction's good. And so this is why this map projection might be useful, because what you can do is you can center it on a particular city, on a particular small area, and then from there, show directions of things. For example, I might want to show a map of Indianapolis Airport and the distances that airplanes travel from that particular point, from our particular airport here. I could use this particular map projection, center the map over Indianapolis, and I could show that, and it would show the directions that the airlines all travel to their respective locations. And I don't really care about the land. These are airplanes. I don't care about the shape. I don't care about the equal area. All I could care about is, from our particular airport, what directions are the airplanes going? What are the distances that they're traveling on those journeys? And here I just moved the central meridian in the latitude of origin here over, this case, Palau, an island country there in the Pacific. I centered the map right here, and you'll notice the distortion gets all crazy, but directions from this particular location are preserved. And of course, like most things, we have a nice blend of things, and so the compromise projection, what it is it tries to manipulate the scale factor so that those extreme angular or area where the shape, size of areas are distorted, tries to minimize them as much as possible. First is the Van der Grinten. This is one in which it's trying to compensate, so it's not perfect, but yeah, I mean the circles are pretty much the same shape. There is some distortion, but the distortion is over here. Yeah, makes Canada and makes Alaska a little bigger than they are in reality. Makes also the Eurasian landmass look much bigger. Russia makes a lot of water area here. Kind of exaggerates things, and so it's not perfect, but it does do a good job of showing things right here along the middle. This is the Robinson projection. This projection shows the whole Earth. We don't see any interruptions like we did with the Goods Holocene. So it's not a perfect equal area. We definitely see some increasing shapes, increasing size, so some distortion there. Also, this could be a problem for some. It does a nice job of separating all this. We can see the Arctic much easier because the North Pole is shown not as a point, which it is in reality, but as a line. But, we can see the shapes of the middle and low latitudes are pretty much good. And so if we think about where do most people live, they live somewhere in this particular area. And so this is why this has become a widely popular map. I believe National Geographic is where you saw this a lot being used when they're showing where various things are located that they're depicting in the images, in the text. Here's the Winkle triple. So this is seen as a bit of an improvement of the Robinson. So we see a little bit less distortion, more of a circle shape instead of an ellipse. So definitely, and so this is why I believe the National Geographic has since said, okay, Robinson, we're done with you. We're not going to use this one. And so those are just some examples of some compromise projections, in which they're not really one of the other ones that I've mentioned. They kind of compromise and they play around with things to make things look as best possible. We also have other ones that are kind of gimmicky. This is one that's kind of shown as a projection as a heart. This one is shown as a star. This here is the most widely used web Mercator, as it's known. It's web Mercator, obviously a cylindrical projection, also a conformal, and it uses the WGS84 coordinate system. This is the online web map essentially because Google Maps is what started using it back in the mid 2000s. So it has some pros and cons. And this is why it's also much maligned in super serious cartography circles because it has a lot of flaws. Why does Google Maps use it? And it's because it does a good job of preserving direction and shape, particularly when you are zoomed into a small area, which once again we call the largest scale. You think about most people who are using Google Maps, they're using it for a specific area. When you're in Tucson, Arizona, and you fire open the Google Maps, you're trying to find where's the nearest museum, where's the nearest restaurant. And you're wanting to know within your specific area, okay, how do I get to those places? And so in the Web Mercator projection, what's nice about it is north is going to be found up, west is always going to be to the left, east is to the right, and south is obviously down. Really not concerned to see as far as distance you are from, let's say, Azerbaijan, or see how big the land area Tucson is compared to some obscure place in Asia. But the cons are that it distorts size and distance, and it does so very bigly. When zoomed out, the high latitude, once again, are exaggerated. This is most definitely not an equal area projection. Thus, this is not what you should be using if you have thematic data in which you're wanting or concerned about showing the land areas in their equal proportions.